you have 2 pair, both of them are used for bounding, that's a linear geometry. 3 pairs, trigonoplanar. Okay. 4 pairs, tetrahedral. 5 pairs, trigonobipyramidal, and then 6 pairs, octahedral. Now, what happens if you have lone pair of electrons involved in here? Well, I'll give you an example there. Now, in this is the situation where the electron group geometry and the molecular geometry are no longer the same. Now, the previous situation, there is no lone pair involved. Every pair is a bounding pair. So the molecular geometry and electron group geometry are identical. Okay? Now, when you have a lone pair of electrons, now two groups of electrons there, and both has to be used, but we can't have a lone pair when you only have 2 pair of electrons on the central atom there. Okay? And you have one central atom, 2 atoms connected to it, so it's a linear structure there. Now, using an example, when you have a 4 valence electron pairs, okay, methane CH4, okay, if you have methane molecule, you have 4 hydrogen, actually 4 atoms surrounding the carbon atom here. The molecular geometry is tetrahedral. Now, if you look at the electron pairs that connecting all of these 4 hydrogen atoms to the carbon atom there, they also take the tetrahedral distribution. Okay, so the electron pair geometry and the molecular geometry are identical when there is no lone pair involved. However, if you look at ammonia, now when you draw the Lewis structure for ammonia, nitrogen is the central atom there, hydrogen attached to it, hydrogen attached to it, hydrogen attached to it. There is a lone pair of electron on nitrogen. Okay, nitrogen group 5A, 5 valence electrons, 6, 7, 8. Total of 8 valence electrons, 2, 4, 6, 8. Okay, all of the 8 electrons are being accounted for. 3 of them are bounding pair. 1 of them is a lone pair. So when you put them into perspective there, nitrogen is the central atom. You have 3 hydrogens surrounding it. Now, these electrons are repelling with one another. Well, you have a lone pair of electrons staying on top. This pair of electrons also repels the other 3 pairs. So each pair of electrons is still repelling all the other 3 pairs there. So in this case, the molecular geometry is trigonopyramidal. Okay? Well, the molecular geometry is trigonopyramidal because the molecule, the ammonia atom in the molecule sits on top, and you have 3 hydrogen atoms surrounding it at the base and forming a triangle shape. Okay, but why is that? Well, simply because this lone pair is going to repel with this bounding pair, with this bounding pair, with this bounding pair. Remember that lone pair to lone pair repulsion is the strongest. Lone pair to bounding pair is somewhere in between. And the bounding pair to bounding pair repulsion is the weakest. So comparing the bound angle, 109.5 in tetrahedral structure in methane, here 107.5. The bound angle gets a little bit smaller. The reason for that is because you have a stronger repulsion between the lone pair to the bounding pair, pushing the bounding pairs closer to one another, resulting in a smaller bounding angle. Okay, so in bound angle there. In this case, the molecular geometry is trigonopyramidal. Electron pair, it's still tetrahedral. You still have 4 valence electron pairs. One of them is bounding pair. The other 3 are lone pairs. Water, as another example. When you draw a Lewis structure of water there, you end up with 2 lone pair of electrons on the oxygen atom. So this is the central atom. Okay. The molecular geometry, if you look at the bound angle there, the molecular geometry, the bound angle is about 104.5 degrees, even smaller than ammonia, and much smaller than methane. The reason for that is because now you have 2 lone pair of electrons. Out of the 4 pairs of electrons there, 2 of them are not being used for bounding. 2 of them are lone pairs. 2 of them are bounding pairs. Now lone pair repulsion, that's the strongest repulsion. Okay, they get the maximum elbow space. Lone pair to bounding pair repulsion is the second strongest repulsion. Okay, so the distance between this pair and this pair and this pair, the bound angle is a little bit larger. The bounding pair, the smallest repulsion, the weakest repulsion. Therefore, the bound angle is the smallest among the 3. Now in this case, the molecular geometry, we call it bent. Okay, we have a bent geometry, molecular geometry, but the electron pair geometry, it's still 1, 2, 3, 4. Total 4 valence electrons. It's still tetrahedral. So with 4 electron pairs, electron pair geometry only depends on how many number of valence electron pairs you have. Whether they're bounding pair or lone pair, we don't care. As long as you have 4 pairs, you end up with tetrahedral. Molecular geometry, talking about the actual orientation of the atoms attached to the central atom, molecular geometry can be different. So we ranging from tetrahedral to trigonopyramidal to bent. So what we have discussed so far is that depending on the situation of the valence electron pairs on the central atom, we should be able to predict the geometry of the electron groups, the geometry of the molecule. What happens if we have more valence electron pairs on the central atom there? Well, when you have 5 valence electron pairs there, all of them are bounding pair, we have trigonal bipyramidal. Okay? Now, if you have 4 bounding pair with 1 lone pair, well, the electron pair geometry is still going to be trigonal bipyramidal, but the molecular geometry is going to be different. So this is the situation when you have lone pair of electrons involved. Lone pair of the electron pair geometry is going to be different from the molecular geometry. Molecular geometry only depends on, the electron pair geometry only depends on the total number of the valence electron pairs. Molecular geometry, you could actually have, when you have 2 bounding pairs and 3 pairs, total of 5 pairs, you could actually end up with a linear molecule. Okay? Because of the distribution, these are 3 lone pairs. They repel to each other, getting their maximum alpha space there, but these 2 atoms are connected to the central atom there. They end up with a linear geometry. So this is a situation where you have 5 electron pairs around the central atom, and the electron group geometry are all identical, trigonal bipyramidal. But the molecular geometry goes depending on the number of total valence, determined on the total number of valence electron pairs, and also how many are lone pairs, how many are bounding pairs. When you have 6 electron pairs, you can have even more complex situation. Now, how do we make predictions there? Well, first we need to determine the total number of valence electron pairs around the central atom. Now, the total number of valence electron pairs is equals to the number of chemical bound. Put a star in there. I'll explain what that star means. Okay. Number of valence number of bounds plus the number of lone pairs surrounding the central atom of interest. Okay. So in this case, when you have a multiple bound, double bound, triple bound, quadruple bound, what have you, all of the electrons in multiple bound will count